In this video, you will learn about dilations. Now, what is a dilation? Well, a dilation is a type of transformation that creates a similar shape by using a scale factor. All right, so with a dilation, the scale factor is represented by the letter K. And so if K is bigger than 1, or the absolute value of it is bigger than 1, that means the object is getting bigger. All right, so because the scale factor is bigger than 1, and that's called an expansion. If the absolute value of K is less than 1, the dilation is called a contraction because it's getting smaller. All right, so because the size is changing, a dilation would not be an isometry, because an isometry requires the lengths or the measurements to stay the same. The only time a dilation would be an isometry is if K is equal to 1, meaning the scale factor is 1 to 1, or the shapes are identical in size, which is not the norm. Okay, that's not what normally happens. So pretty much all the time, or most of the time, a dilation will not be an isometry. Now, with notation of a dilation, we use the first letter of the word dilation. So we use letter D to represent a dilation. And then we have a center point, and then we have the scale factor. So O is the center in this case, and the scale factor is the letter K. So typically, K is going to be just some number. It could be a fraction, could be negative even, and then the center doesn't have to be the point O. It could be a different point. It could be point A, B, C, etc. So how do you create a dilation? Well, let's look at our first example where K is going to be positive. All right, and we're going to look at an expansion as well. So what we're doing in this case is we're trying to find the image of triangle ABC under the expansion D and then sub O, 2. So this notation means that we have a dilation where the center point is O, and we are creating a triangle or a shape that is twice as big. The 2 means the scale factor is 2 to 1, so the new figure is twice as large as this original figure right here. So to create a dilation, what you do is you use the point O, and you draw a line, or I guess a ray, through point O and through A. So from O through A. And then we do that for all the vertices. So from O through B, and then O through C. Okay, and what we do is we find the length from O to A, and then we create a segment twice as long as that. So from O, we're going to go up here to find our point. So the segment from O up to here is twice as long as from O to A. And when you're doing this by hand, you could use a compass, or you can use a ruler even to measure those amounts. And then from O to B, we measure that amount, and then we have to go twice as far as that. So we can go up here to this location. So from O to this point is twice as far as from O to B. Do the same thing with this last vertex. So from O to C, we want to go twice as far as that. So we go up here to this vertex, this point. So the distance from O to this point is twice as far as from O to C. And then we connect the dots. So we connect the dots, and we have now our new triangle. And we can call this A prime, B prime, and C prime. So a few things about this picture that we've created. So first off, in notation, we can say that triangle ABC is mapped to triangle A prime, B prime, C prime under this dilation over here. All right, and with this, these two triangles we've created are similar. So we can use our similar symbol, which is this squiggly line. So these triangles are similar, which means that the sides are in proportion, they're in the same ratio, and the angle measures are the same. All right, so like this angle here is the same as this angle up here, and etc. So also with this, we know that the distance the segments for each triangle is going to be in the same ratio, and we know that A prime, B prime, this segment up here, is going to be twice as long as AB, this segment right here. It's twice as large. And that goes for every side length. So B prime C prime over here, that is twice as large as BC over here. And then A prime C prime is twice as long as AC. All right, so that's because of this dilation that we've created with a scale factor of 2. That is why it's twice as large for each side. Okay, and also, as we've kind of mentioned as we created the picture, the distance from O to A prime is twice as far as from O to A. And then from O to B prime is twice as far as from O to B, and O to C prime is twice as far as from O to C. One other thing with the sides that we have created, notice that each corresponding side is parallel to each other. So for example, this the segment AB, that is parallel to A prime B prime. And then same thing for the other segments as well. So BC over here, this right side, is parallel to B prime C prime. So these two sides are parallel, and then AC and A prime C prime, those are parallel as well. All right, so that's a few things to take note of in this picture we've created, and all these relationships will be pretty much the same with any dilation we create. We have parallel sides created, and the side lengths will be all the same ratio. All right, it's going to be created by this dilation. Now, what if K is negative? So here we have a negative K. Well, what we're trying to do is, again, find the image of triangle ABC, but here we have the dilation of center of 0, and the scale factor now is a negative 1 over 2. So what the negative does is it changes the direction. All right, and the 1/2, what that does, because it's smaller than 1, is it's creating a smaller triangle. All right, so because it's a negative number here for the scale factor, what we need to do is we're going to create a shape down in this area. So before it was up in the middle, like up in here, or beyond it up in this area, but we need to go on the other side of the center point because of the negative. So to create this, you're going to take each segment or each vertex A, B, and C and create a ray through the center point like this. So what we're going to do is we're going to put the 3 vertices somewhere over here on this left side of the origin, and it's going to be somewhere on each of these rays. So to find the exact location, we need to find the distance from the center to each of the vertices. And then we're going to take half that distance and go that far down here on this bottom part. So what that looks like would be something like this, where we measure the distance from O to A, and then find half that length and go to find A prime down here. So from O to A prime, that's half the length of OA. And then O to B prime is half the length from O to B. And O to C prime is half the length from O to C. So we measure those to find these different points, and then connect the dots to get this new triangle right here. So what we have done is we've created now 2 similar triangles, where under this dilation, with the center at 0 and the scale factor being negative 1/2, triangle ABC is being mapped to triangle A prime, B prime, C prime. And we've created similar triangles, so we see the similar symbol right here. And as we've mentioned, the side lengths are going to be to that scale factor as well. So like A prime, B prime, that is half the length of A to B. And then same thing for the other side. So from B prime to C prime on this triangle down here, that's half the length of B to C. And then A prime to C prime, that's half the length of A to C. So that 1/2 comes from the scale factor we see up here. And as we've mentioned when we created this, that O to A prime is half the length of O to A, O to B prime is half the length of O to B, and O to C prime is half the length of O to C. All right, and still, even though the dilation with the negative scale factor flips the triangle over to this side, the corresponding sides are still parallel. Right? If you look at A prime, B prime, right here, that is parallel to AB up here. And then B prime, C prime over here is parallel to BC over here. And then A prime, C prime is parallel to AC. So we still have parallel sides even though the dilation has a negative scale factor. Now for all these examples that we've done so far, the center point has been outside of the shape. All right, so now on this next example, we're going to finish off with a picture where the center point is inside of the figure. So here the center point is point O, and what we're trying to do is find the image of triangle ABC under, this shouldn't say expansion, it should be dilation. It's not expanding, it's getting smaller. But we're creating a dilation such that we have the center point at O, and the scale factor is 3/4. So it's still going to be the same logic as we did for the other sketches. So we use the center point and create a segment to each of the vertices. And what we do is we measure the length from each vertex to the center, and then find 3/4 of that to find our other points. So for example, it's going to look like this. And we find these points because if you measure from O to A, you find the length, take 3/4 of that to find how far to go to find this point right here. And then same thing from O to C, measure that length, and then find 3/4 of that to figure out how far to go for this point down here. And lastly, for O to B, same thing, we find 3/4 of that length, and we use that to find this point right here. And then we have our three vertices, and we connect the dots, and we now have A prime, B prime, C prime. So this triangle we've created, it came from this dilation here with the center O and the scale factor 3/4. So it maps triangle ABC to triangle A prime, B prime, C prime. We still have congruent triangles, as we can write right here in this notation. And each of the sides are 3/4 of the original side. So we see that typed up right here, where A prime, B prime is 3/4 of the length of AB, B prime, C prime is 3/4 of the length of BC, and A prime, C prime is 3/4 the length of AC. Okay, and as we've mentioned when we created those points to find the vertices, okay, O to A prime is 3/4 of the length from O to A, O to B prime is 3/4 of the length as from O to B, and then O to C prime is 3/4 of the length from O to C. And as we've mentioned with dilations, the corresponding sides will also be parallel. So we see that typed up down here. AB is parallel to A prime, B prime, and then BC is parallel to B prime, C prime, and then AC is parallel to A prime, C prime over here. So in this lesson, we've learned about dilations. We've learned also how to create dilations. And that concludes our lesson for today. We will see you next time.